Welcome back, guys. So today we'll discuss some problems from the second paper. So first question was from dimension analysis. So they're mentioning a temperature difference can generate EMF in some materials. So let S be the EMF produced per unit temperature difference between the end of the wire. Okay. So basically, for the purpose of deriving the dimensions, we can just write S as V divided by T. V is in volts, T is in Kelvin. Sigma, they're saying, is the electrical conductivity. So we need the dimensions of V by T squared times sigma. Sigma, we can say, so we can write V equals IR. So V equals I times rho 1 by sigma times L by A, which is just length, like 1 by length. So sigma is I divided by V into L, and that thing divided by the thermal conductivity. So that we can relate it using the heat current formula. So the heat current dq by dt. dq by dt is energy by time, so that's just power. Power we can relate it using I into V. So this would be equal to, this is equal to ka dt by dx, right? So this would be k times a by dx is just length, and temperature dt we can just write it as T for now, as we only care about the dimensions. So from here the dimension of k is IV divided by LT. Okay, so I cancels, V and V cancel out with this V, the L also cancels out, and then what we're left with is 1 over T. So that is Kelvin inverse. So yeah, that's it. Now let's move on. So problem 2 is a pretty similar problem which we often observe in different EITs. Yeah, basically we have two coaxial conducting cylinders of the same length L with different radius root 2r and 2r. The charge on the inner cylinder is Q and the outer cylinder is grounded. The annular region between the cylinders is filled with a material of dielectric constant kappa equals 5. Okay, so we have a dielectric material inserted between these two cylinders. Consider an imaginary plane of the same length L at a distance r from the common axis of the cylinders. The plane is parallel to the axis of the cylinders. The cross-sectional view of this arrangement is shown in figure 2. Ignore edge effects. The flux of the electric field through the plane is. Alright, so firstly, there won't be any electric flux through this rectangle, right? Because there's no field there, right? So the electric field will only be present in the region of the dielectric, and there won't be any electric field outside as well because the outer cylinder is grounded. You can think of it like, as the outer cylinder is grounded, we are basically making it the same potential as that of Earth. So there shouldn't be any potential drop between the outer surface and a point which is tending to infinity. And if there shouldn't be any potential drop in this region, that means the electric field here should be 0. Otherwise, integral E dot dl will be non-zero. Okay, so now you can either take a Gaussian surface, which looks something like this. Okay, through this Gaussian surface, of course, none of these points matter because there's no electric flux over there, as there is no field over there. Similarly, these points also don't matter. The flux contribution is only at the location of this rectangle, this rectangle, this rectangle, and this rectangle. Okay, so this flux will be proportional to the total charge enclosed within this Gaussian surface. So we can either do that, or we can just quickly prove the fact that the flux through this rectangle is basically proportional to the angle that it subtends at the center. So we can just draw parallels to this particular problem where we have a line charge at the center along the axis of a cylinder, and we have to find the flux through this particular plane. Okay, so the flux through this particular surface is basically the same as the flux through this surface, right? So basically you can take this thing as a Gaussian surface. So the phi through this surface should be the same as the phi through this surface, as there's no enclosed charge, right? And the flux through this particular section of the cylinder, it will be proportional to the angle that it subtends at the center. Okay, and that we can easily say using symmetry, right? As the electric field lines are equally distributed in the radial direction. If this particular line subtends an angle theta at the center, we can say that the total flux through the plane or through this part of the cylinder is going to be theta over 2 pi times q enclosed over epsilon naught. Okay, so yeah, if you know this basic result, then if you remove some section of the cylindrical plane, then the final answer will depend on this angle theta 1 and this angle theta 2. That's it, right? Using the exact same argument. So you just have to figure out what is the angle that this segment subtends at the center, and then that would be it. So if you connect these 2 points, so this is capillary and the outer radius is 2r, so this angle is 60, and similarly if you connect these 2 points, so here this angle is going to be 45. Okay, so the angle that this rectangle subtends at the center is going to be 15 degrees. Similarly, even this rectangle will subtend 15 degrees at the center. So in total, the angle subtended would be 30 degrees. So the flux, we can write it as 30 over 360. This is the angular fraction. This multiplied by the total electric flux. So that would be Q by epsilon of the media, which will be epsilon naught K. Why is it? Because the radial electric field in this region, it will become the original electric field by K. So the flux of that electric field will also get divided by K. Okay, an alternate way to look at this will be, you can take this thing as the Gaussian surface. So if you take this as the Gaussian surface, then once again flux is only going to be emanating from this particular surface. Okay, because the other two sides are in the radial direction, so the electric fields are going to be parallel to it. So the flux through this surface will be Q enclosed by epsilon naught, and the Q enclosed is in this part, right? And here you have to be careful because the Q enclosed will include the polarization charges as well. So the actual charge present there plus the polarization will be Q by K. So the actual free charge will be Q multiplied by 15 divided by 360. This will be the actual free charge in this location. This thing divided by K. So this will be the total free plus polarization charge. So this is the total charge enclosed within this Gaussian surface. We'll just multiply this with 2 to account for this surface as well. And yeah, that is basically the same as that. Okay, so yeah, there could be multiple ways. It doesn't matter which way you do. They're all similar anyway. So yeah, from here, I guess you get, so we have a 1 by 12 factor and 12 i's are 60. So the answer will become C option. So in problem 3, we have two figures in which we have a uniform rod OO dash of length L that is hinged at point O and held in place vertically between two walls using massless springs of spring constant. The springs are connected at the midpoint and at the top end of the rod in figure 1. Okay, so basically in these two situations, they are made to oscillate with small angular displacements, and we have to compare their frequencies. Okay, so basically as the hinge remains fixed. Okay, so basically we have to compare the restoring torques, right? As the moment of inertia of the rods in both configuration remains the same. So we just have to compare the restoring torques in both the situations. So if you displace this by theta in the counterclockwise sense, this spring approximately compresses by L by 2 theta. And this spring elongates by L by 2 theta. So in total, the force is L theta. So L theta multiplied by L by 2. So we can use factors here. So here we see a total factor of half, right? KL theta multiplied by L by 2 is the torque. So I am just including that half factor because we just have to compare the torques. Here the force on this spring is once again KL by 2 theta multiplied by L by 2. So we have a factor half, and this will get added with, so this spring is elongated by L theta, and L theta into L is the net torque because of this spring. So here we have a factor of 1. So 1 plus 1 by 4 is 5 by 4. Okay, so now of course the frequencies are going to be proportional to the square root of tau 1 over tau 2. That is going to be square root 5 by 4 over half, which is 5 by 2. Okay, so the answer is going to be C option. Okay, so the story of this problem is similar to last year's IPHO problem. So it was called a black widow pulsar or something like that. So in the problem, we have a star whose mass is M2, which is revolving in a circular orbit around another star of M1. Okay, so we have a star of M1 over here, and the M1's mass is significantly greater than M2. Okay, so we can consider the barycenter to be, or the common center of mass to be around the center of M1 itself. So that the motion that we are going to be observing is M2 moving around in a circular orbit where M1 almost remains fixed. Okay, in the frame of the center of mass, of course. So in this case, of course, as it's orbiting in a circular orbit, its speed will be the orbital speed, which is square root g m1 by r. Okay. Now it's given that the heavier star slowly acquires mass from the lighter star at a constant rate of gamma. In the transfer process, there is no other loss of mass. If the separation between the centers of the stars is r, then the relative change of 1 by r times dr by dt. Okay, so firstly, they mentioned that the mass acquiring process is slow. Okay, so now the thing is, we'll just conserve the angular momentum of the system because, mainly we have the central force of the gravitational force acting on mass m2, which of course does not contribute to any torque about the center of mass. And other than that, we can neglect the contribution of angular momentum due to the negligible tiny mass that is flowing towards M1. We can neglect their contribution in compared to the contribution of M2. So if we conserve the angular momentum of the system, M1 is practically at rest. So the angular momentum is just M2 into its speed, which is square root gm1 over r, multiplied by the radial distance from M1, which is r. Okay. Yeah, now we'll just differentiate and equate it to 0 because the angular momentum is conserved in this situation. And also we'll of course use log because that tidies things up in this particular situation. So we have ln m2 plus ln of m1 half ln m1 plus half ln of r. So yeah, now we'll just differentiate it. L dot over L, the L dot is going to be 0. Okay, and we have m2 dot over m2. Now as the mass that is lost by m2 is gained by m1, we can if we say m1 plus m2 is a constant, then m1 dot plus m2 dot is going to be 0. Now it was given that m1 dot was gamma, so m2 dot is negative gamma. Okay, m2 dot is negative gamma divided by m2 plus half of this will be m1 dot, which is gamma over m1. So this will be 1 by r times r dot. So now the thing is, out of these two terms, we'll neglect the insignificant term, which in this case is gamma over m1 because m1 is significantly larger than m2. So from here, r dot over r is coming out to be plus 2 gamma over m2. I mean the matching option is B, but here we have a negative sign, which I think is a mistake. And I just went back to the IPHO problem as well. So there the final solution given for r dot over r is negative 2 m1 dot over m1 times 1 minus m1 over m2. So it's given to be this particular expression. So okay, and here m1 is the one that is gaining the mass and m2 is losing the mass. So if we neglect this thing, we obtain the same value. So I think it should be a positive instead of a negative. So basically the distance r would increase rather than decrease. Okay. So yeah, that's question 4. So in question 5, we have a point charge of 10 to the power negative 8 coulomb that is kept at a distance of 20 centimeters from the center of a neutral conducting sphere. Okay, so let's draw the neutral conducting sphere and a point charge of charge 10 to the negative 8 coulomb. So, okay, and the distance from the center of the shell is given to be 20 centimeters. The sphere is then grounded and the charge on the sphere is measured, and then the grounding was removed. Subsequently, the point charge is moved by a distance of 10 centimeters further away from the center of the sphere along the radial direction. So which of the statements are correct? So before the grounding, the electrostatic potential of the sphere is 450 volt. Okay, so this is just a standard problem. So we just know that at all the points inside, the electric field is 0. So there is no potential difference between the center of the sphere and the surface. So we'll just figure out the potential at the center of the sphere. Okay, and that will basically be the potential of the sphere as well. Okay, and it's easy to figure out the potential at the center using superposition. The contribution due to this charge is just kq divided by r. So that would be, so if I take k at 9 into 10 to the power 9, q is 10 to the power 8 divided by 20 centimeters. So it'll be 900 by 2, which is 450 volt. So now the thing is, this positive charge will attract, more negative density towards this side, and there would be deficiency on the other side. However, the charge distribution is, it will be neutral at the end of the day. So if you figure out the total potential contribution due to all these charges at the center, it will be k times sigma q divided by r, right? And sigma q would be 0 because it's a neutral sphere. So therefore the net contribution due to the surface charges and this 10 to the power minus 8 coulomb charge at the point O will be 450 volt. So 450 volt will be the potential of the sphere as well. So option A would be correct. Okay, so now the thing is, charge flowing from the sphere to the ground because of grounding. Okay. You're setting the potential of the sphere to 0. So basically the value of the potential at the center of the sphere should also become 0. So which means the original contribution, so we already figured out the potential contribution due to this plus q charge at the center was 450 volt. So the contribution due to the surface charges at the point at the center should also be 450. So we can just do 450 equals k times q net on the sphere divided by capital R, which is the radius of the sphere. Okay, and in fact it will be minus 450 because plus q contributes plus 450. The surface charges should contribute minus 450 so that the total becomes 0 at the center. So the q net on the surface of the sphere will be 5 into 10 to the power minus 9 coulomb. So which means the charge flowed from the sphere to the ground, right? Or in other words, we can say this amount of positive charge flowed from the sphere into the ground. So option B would also be correct. In option C, they're saying after the grounding is removed, the charge on the sphere is negative 5 into 10 to the power minus 9 coulomb. Yes, of course, this is also true. So I don't understand the point behind this option. It's basically option B itself. Then option D, they're saying the final electrostatic potential of the sphere is. So once again, what they did was after it was removed, subsequently, the point charge is moved a distance 10 centimeter further away. So we pick the original point charge and move it by 10 centimeters away. And now we have to figure out the final electric potential. So the new contribution due to the point charge is going to be 450 multiplied by 20 divided by 30. So I'm just doing ratio and proportion. So the new final distance is 30. Original was 20. So the potential will scale by a factor of 20 by 30. So 150 into 2 is 300 volt. So 300 volt is the potential at the center due to the 10 to the power minus 8 coulomb charge. And because of the original charge distribution of minus 5 into 10 to the power minus 9, it will be minus 450 volt. So the final electric potential at the center will be minus 150 volt. Okay, so the minus 450 by the sphere and the plus 300 by the point charge. Finally, it will be minus 150, not 300. So this is going to be wrong. So in problem 6, we have two identical concave mirrors, each of focal length f, and they're facing each other as shown in the schematic diagram. The focal length f is much larger than the size of the mirrors. A glass slab of thickness t and refractive index n0 is kept equidistant from the mirrors and perpendicular to their common axis. A monochromatic point light source S is embedded at the center of the slab as on the principal axis. For the image to be formed on S itself, which of the following distances between the two mirrors is/are correct? Okay, so basically if we consider any ray after refraction from the slab that intersects the concave mirror, so one potential way is of course this particular ray becoming parallel to the principal axis, and after this it collides with the second mirror, and by symmetry it will intercept the slab at the other symmetric point, and then it will refract and hit the center once again. Okay, so now if this particular ray after refraction is parallel, then that would mean that the originating light ray originated from the focal length of the lens, right? So okay, so now the thing is after refraction from the first surface, if we consider the shift due to the slab, so the source is kept somewhere over here. So if we consider the refraction at this particular surface, and because of refraction we have a parallel shift of the light source or the distance of the source from the mirror. So we want this distance from the mirror to be equal to the focal length. Okay, and the shift is of course equal to the thickness. So this particular thickness is t by 2. So the shift would be t by 2 into 1 minus 1 by mu. So in the question they asked what is the distance between the mirrors. That will be just the double of this value. So that would be 2f plus t 1 minus 1 by mu. Okay, so that would be option B. Now another possibility is that this particular light ray, it intercepts the concave mirror perpendicularly. Then of course this light ray will be sent back, and then after refraction the final image will be formed at the source itself. Okay, so now for this particular situation to happen, this length should be equal to the radii of curvature of the mirror, which we can consider it as 2f because we are talking about a concave mirror. So which means the distance of the new source from the optical axis would be 2f. So 2f plus t by 2 1 minus 1 by mu is the new distance from the source to the optical axis. So just double that. So that will give you the answer as 4f plus t1 minus 1 by mu. Okay, so basically adding 2f to the answer, so that will give A option. So in problem 7 we have 6 infinitely large and thin non-conducting sheets that are fixed in configurations 1 and 2. So the sheets carry uniform surface charge densities which are indicated in terms of sigma naught. The separation between any two consecutive sheets is 1 micrometer. The various regions between the sheets are denoted as 1, 2, 3, 4 and 5. Sigma naught's value is given, permittivity of free space value is given. You have to choose the correct statements. So in option A, they are asking in region 4 of the configuration 1, the magnitude of the electric field is 0. Okay, so you just have to consider superposition rule here. So the electric field due to this plus and minus, they mutually cancel each other at this particular location. Now due to this plus and this minus also, they mutually cancel each other out. And due to this plus and this minus also, it mutually cancels each other out. So of course the field is going to be 0. Okay, and if you guys didn't understand, because of this plus sigma naught, the field here will be sigma naught by 2 epsilon naught, right? And because of this negative sigma naught, it will be just the reverse of it, and they mutually cancel each other out. So the plus and minus, they mutually kill each other, right? So similarly, the other two plus minuses also kill each other at the location 4, and the answer is 0. In region 3 of the configuration 2, the magnitude of electric field is sigma by epsilon naught. Okay, so over here. Okay, now here you have to be a bit careful. These two kill each other because they're on the left side of 3, and these two kill each other because they're on the right side of 3, but these two don't mutually kill each other, right? Because they in fact add up. So because of the sigma by 2, we have a sigma naught by 4 epsilon naught towards the right, and because of the negative sigma naught by 2, we'll have a sigma naught by 4 epsilon naught to the right as well. So this will be sigma naught by 2 epsilon naught, but in the option it's mentioned as sigma naught by epsilon naught, which would be wrong. Potential difference between the first and the last sheets of the configuration is 5 volt. Okay, so yeah, we also had to figure out the potential difference. Okay, so now as we have to determine the fields in each location, we can just assume the charge distribution for the conductor, right? So if I say this is 0, sigma naught, this is negative sigma naught, 0, 0, sigma naught, minus sigma naught, here once again 0, 0, plus sigma naught, negative sigma naught, and 0. So if I assume this, it wouldn't make any difference because once again, if you consider the entire plate, its electric field will still be sigma naught by 2 epsilon naught to the right at any point to the right? So of course this makes the calculation easier. Now the electric field here will be just sigma naught by epsilon naught, here it will be 0, and here also it will be sigma naught by epsilon naught, here also it will be sigma naught by epsilon naught. Okay, of course the field here will be 0. Okay, so you can basically split the charge however you want. Okay, so you can, even if you split it like sigma naught by 2, sigma naught by 2, you'll get the same answer. Okay, but of course this doesn't help simplifying it. If you can assume it however you want, you might as well assume it like the conductor one, because then you can just directly say that the field between the plates will be just dependent on this sigma naught, okay, and not the others. Okay, so you can do the same thing for here as well. Now they're asking the potential difference between the first and the last sheet. So the magnitude of potential difference will be 3 ED basically, right? So for C option, delta V is 3 times the electric field, which is sigma naught by epsilon naught. Sigma naught is 9 microcoulomb per meter square. Epsilon naught is 9 into 10 power minus 12. It will be 10 to the power 6 times D, and D was given to be 1 micrometer. So the answer is 3 volt. Okay, so C would be wrong. Now potential difference between the first and the last sheets of the configuration 2. So once again we'll assume the configuration of the conductor. So we have sigma naught by 2, minus sigma naught by 2, minus sigma naught by 2 here, plus sigma naught by 2 here. We'll have a plus sigma naught by 2 here, a negative sigma naught by 2 here, negative sigma naught by 2 here, plus sigma by 2, and finally a minus sigma by 2. Okay, so if we zoom in, here we have sigma naught by 2 epsilon naught. Here the electric field is like this. So it's like alternating, right? What they are asking is the potential difference between the first and the last. So of course this is going to be just E into D. So sigma by 2 epsilon naught, this is the electric field, times D. Sigma by epsilon naught was 10 power 6. D was 10 power minus 6 divided by 2. This will be 0.5 volt. And so of course D option will be wrong. So yeah, that was it for this question. So yeah, if you guys have any doubts, you can ask below. If you enjoyed the video, make sure to like, share and subscribe. That's it. Thanks for watching.